Hello all of you. So we're going to have a look at oblique collisions. What exactly are oblique collisions? Well, it's one where you have an object, two or more objects rather, which are going to collide such that the line of impact is not along uh, the center of masses of the two objects. Look here. I have object A moving along this line. And for the sake of simplicity, we're going to take object B, the sphere B, as being stationary. The center of mass of A is here, center of mass of B is right here. For a one-dimensional collision, the objects would be moving along a line joining the centers of mass. But this is not the case here. The line of impact here, which is the line along which object A is moving, is some distance from the center of mass of B. So what will happen when they collide? You're going to get something as follows. You're going to have a two-dimensional motion. Both A and B are going to have velocity components along the initial line of impact, but they will also have velocity components perpendicular to it. That is, their respective velocities are going to be at an angle to the line of impact. You can see here, object A will move velocity VA at an angle alpha. Object B will move velocity VB at an angle beta from the line of impact. Okay? So we have an example here. I would strongly advise you to go to this site. There are a lot of simulations that will be very helpful for you. I have object 2, sphere 2, initially at rest. Sphere 1 is going to be moving towards sphere 2 and collide with it. You can adjust the masses here of the two objects, adjust the velocities, etc. Let's see what is going to happen. So they collide, and after collision, one moves in this direction with a particular velocity, two moves in another direction. You can see that the two velocities are no more aligned, so we have a two-dimensional problem now. It's also good to have a look at the momenta. In black here, you have the initial momentum before collision. And if you look here, this is labeled 1. This is the after collision. This is the momentum of the sphere 1. And this is the linear momentum of the sphere 2. From conservation of momentum, resultant momentum or total momentum after collision must be the same as the initial momentum. So we have a closed vector triangle. This is going to become very useful when solving problems. So let's get back to this small problem here. So our two spheres A and B colliding with each other and moving outward. Now, if I want to find the velocity of one of the objects after collision, I will need to be using conservation of momentum, whether the collision is elastic or not. To keep things simple, we will assume that we know one of the velocities at least and one of the angles. So let's have a look at, if I have to write equations for conservation of momentum, how this is going to be. So I need to consider two different directions. First direction, along the line of impact. Second direction is going to be perpendicular to the line of impact. Let's take the right as being positive. And for the perpendicular direction, we're going to take up in the diagram as being positive. So momentum after collision is equal to momentum before collision. After collision, momentum of A along the line of impact is going to be MAVA cos alpha. Similarly, for B is going to be MBVB cos beta. Notice that both components are to the right, that is, both are going to be positive. This is going to be the same as the initial momentum before collision, which is going to be mass of A times the initial velocity. The initial velocity is already along the line of impact here. So if you look at the result, we're going to obtain this equation. Now, if we resolve perpendicular to the line of impact, we get something like this. Again, momentum is going to be conserved along any direction. So the linear momentum after collision is going to be equal to the momentum before collision. We're going to get this. Let me explain it. A is going to be moving downwards in the negative direction. Its momentum is going to be MAVA sine alpha, but with a minus sign, which you have here. For B, it's going to be MBVB sine beta. It's going to be upwards, the positive value. And this is going to be equal to, before collision, 0. Why 0? Because before collision, there's no motion at all perpendicular to the line of impact, so there's no momentum perpendicular to the line of impact. So we have two equations, and we're going to use these equations to try to solve problems. Now, I've kept things simple here, meaning that B is initially stationary. In practice, B could also be moving. Let's have a look at an example. We're going to solve this example using two methods. First, by resolving, and second, by drawing a vector triangle for conservation of momentum. So you have the masses of A here, 0.20 kilogram, mass of B, 0.30 kilogram, the initial velocity of A, 12.0 meters per second. B, we're going to take it as initially at rest, that is stationary. After collision, let's say I have this situation. I'm going to have B moving at an angle of 40 degrees from the line of impact with a velocity of 5 meters per second. For A, we don't know the velocity and we don't know the angle, alpha. So how are we going to solve this now? We have seen previously, just apply the principle of conservation of momentum along two different perpendicular directions. So we need to resolve. So this is along the line of impact. All the components are positive here. You can check the substitution. We're going to be left with this equation. I'll let you go over the substitution and simplification on your own. Right? It's one equation, two unknowns. We can't solve, obviously, so we need to have a second equation. We can apply the principle of conservation of momentum perpendicular to the line of impact now. So I'm going to take up as positive. For B, it's going to be MBVB sine 40 degrees, sine beta, which is going to be 40 degrees. This is the substitution here. A is going to be moving the opposite direction. Let me take that as negative. Minus MAVA sine alpha. So we simplify. I let you do the simplification. We are left with a second equation. VA sine alpha is equal to 4.821. This is equation 2. So we have now two equations, 1 and 2, with the same two unknowns, two equation, two unknown. We should be able to solve simultaneously. First thing, I think the easiest thing to do is to find alpha. I can have equation 2 divided by equation 1. The VA will be eliminated. Sine alpha over cos alpha is simply tan alpha. So I get tan alpha here. And I can solve for alpha. It's going to be 38 degrees. Similarly, once we get alpha now, we can substitute in any of the two equations. I've chosen equation 1, you can choose equation 2. You can find a value for VA, and I'm going to get 7.90 meter per second. Now, you may be wondering, is this equation elastic or not? The only way to check it is to have a look at whether the kinetic energy is conserved or not. We can't really be using relative speed of approach is equal to relative speed of separation because we're now having a two-dimensional problem. So let's have a look here. Before collision, only A is moving. We can calculate the kinetic energy as 14.4 joules. After collision, I have the speeds of both A and B, means I can find the total kinetic energy. Again, I let you go over the calculation. I'm going to get 10.0 joules. Means that after collision, the kinetic energy is less than before collision. Hence, the collision is definitely inelastic. Now, let's have a look at a second method. I'm going to use a vector triangle to find the final momentum. The initial total momentum before collision is Pi. The final momentum of A after collision is PA, and the momentum of B after collision is PB. If I have to write an equation in the vector form, it's going to be as follows. Initial momentum is the sum of the two momenta after collision. It's a vector addition, not a scalar addition. Means you need to take direction into consideration. Let us find what we know. I know the initial, je peux trouver the size of the initial momentum. If you work it out, mass times velocity, ça fait 2.4 kg meter per second. Same thing for B. The magnitude of the momentum is going to be the mass of B times the speed of B, 1.5 kg meter per second. So we can now draw this very simple vector triangle and use trigonometry to solve. I let you have a look at the triangle for a short while. So let's have a look at this. Pi, the initial momentum. If momentum is to be conserved after collision, if I add momentum of A and momentum of B, I should get the same value here, the same vector. So PA plus BB is equal to PI, which satisfies the conservation of momentum. Now, initially, momentum of A is along the line of impact. From the problem here, we know that B is going to be moving at an angle of 40 degrees from the line of impact and A at an angle alpha. So definitely B is going to be at 40 degrees here. Basic mathematics, this forms a Z alternate angles. Angle theta are at 40 degrees. And this is angle alpha. So I have a nice triangle. I know this angle here 40 degrees and I know these two sides. So we can use the cosine rule. Here's the application of the cosine rule. Again, I let you go over the mathematical part. We solve, and we're going to get the size of the momentum of A, 1.58 kilogram meter per second. Now, momentum of A is simply the mass of A times velocity of A. And when we add this here, mass of A is 0.20 kilogram. What do we get? 7.90 meter per second, which is indeed what we got using the method by resolving. You see what method you prefer, huh? Whether you prefer resolving or draw the triangle, use trigonometry, it's up to you. Now, to find angle alpha, you can use the sine rule. Sine alpha over the opposite side, which is going to be PB, is going to be equal to sine theta. We know theta is 40 degrees over PA. We have calculated PA. So you can substitute the values here, and I'm going to get 37.6 degrees, 38 degrees, which is exactly what we got here. So you have two methods to help you go along these problems. Another example now. Again, the collision is going to be inelastic here. Have two objects, x and y, move along perpendicular lines are shown here. X is moving to the right here, y is moving upwards. Eventually they collide. Now, before I have a look at how to solve it, let's calculate the magnitude of the momentum. 30 kilograms times the speed times the velocity is going to be 180 kilogram meter per second. This is just the magnitude. Hein? Py, pareil, mass of y multiplied by the velocity of y, 150 kilogram meter per second. 150 kilogram meter per second. After collision now, let's assume that the two objects stick together. Maybe they are magnetic, for example, or maybe they are made of some sticky substance, so they stick together. Imagine two spheres made of plasticine moving, they collide, they can stick together. After collision, the two objects stick together and move as shown. So I have a common velocity v, and this velocity makes an angle theta with the horizontal direction. That is the direction along which x was initially moving. Now the two objects are just one. I can find the combined mass, 80 kilograms. The magnitude of the final momentum is going to be equal to mv. That is 80 kilograms times v. We don't know v. We call this pf. This is easier than the example we have seen previously because now we do have an angle which is 90 degrees. I can draw a vector triangle. This is momentum of x before collision, momentum of y. When I add it, I should have the final momentum, pf. So I obtain a nice right angle vector triangle. Whenever you see triangle, you hear triangle and right angle, you know that Pythagoras theorem will come in handy. So from the principle of conservation of linear momentum, again, I write this vector equation. And this is the triangle corresponding to this vector equation. We have already found the magnitude of px and py. Use Pythagoras theorem, on va avoir ça. 234 kilograms meter per second as the magnitude of the momentum, of the total momentum. I'm going to use this. Pf is equal to ATV. To find v, v is going to be equal to 2.92 meters per second. And of course, I need to find the direction of this momentum. So I'm going to find the angle theta. You can use sine, cos, tan, whatever you prefer. I'm using tan. So tan theta is going to be equal to py over px, opposite over adjacent side. So we are going to be obtaining this 39.8 degrees or 40 degrees. So I hope you find this explanation useful, and we'll continue, hopefully in class.